This is the fourth lecture on the lateral equations, and in this lecture we will look at the initial response to an Aileron deflection. And in principle, this is a dynamic analysis, and we will see how to analyze the aircraft dynamics in response to a simple control surface deflection. In here is Aileron deflection. Okay, and so in this lecture, we will try to answer this question: how will the aircraft respond to a simple deflection of aileron? And we see a rear view of the aircraft, and also we see the deflection of the aileron, and the left aileron deflected downward, and while the right aileron deflected upward. So in this case, the aircraft will start to roll, and the deflection angle is delta A. So the aircraft start to roll at a rate of P. That's a rolling rate. Okay. So in this case, usually there is a side slip velocity produced, but in here, and we make assumption that there's no side slip velocity. So make the case easier to discuss. Okay, so let's see the sequence. And first you have aileron deflection, delta A, and then the aircraft start to roll at a rate of P. So it's a positive rolling rate, P, positive P. And in that case, a restoring moment will be produced. And the restoring moment is LP times P. That's a rolling moment due to the rolling rate. Okay, so now let's see how do we write down the governing equations. And we can see there are two contributions to the rolling rate, rolling moment. One is from the aileron deflection, the other is from the LP. That's the rolling moment change due to the rolling rate. Okay, so we have the governing equation. So the left is following the Newton's second law. Okay, so on the right hand side, that's the two components, two contributions, one from the LP, the other from aileron deflection. Okay, so we move because the answer of this governing equation is we want to have an explicit expression of P in relation with time. Okay, so then P is the unknown. We are interested. We are moving P towards the same left-hand side. Then we are having this governing equation in the bracket. Okay, so let's do some observation of this governing equation. This is a first-order linear differential equation, and the solution for this equation follows the summation of two components. One is CF, the other is PI. What is CF? CF is a complementary function. PI is a particular integration. Okay, so the next steps are to find how to determine CF and PI. Now let's determine how to find the CF and PI respectively. Okay. So let's first look at CF complementary function, and in order to find CF, we need to making the right-hand side of the equation being 0. That means the forcing function is 0. So that's what we need to do. And what does that mean, forcing function? So we can see the forcing function includes the deflection angle. So this maneuver is excited by the aileron deflection. That's why we call it forcing function. Okay, so making the forcing right-hand side being 0, and we have the equation like this. So the right-hand side is 0, and we know P can be expressed in the form of k times e to the power of lambda t, and then the first order derivative of P is k times lambda times e to the power of lambda t. Okay, so now we have P and we have P derivative. So we plug into the equation. So we have this, And if we take the common part out, which is k times e to the power of lambda t, and so k times e to the power of lambda t can't be 0, so the coefficient part should be 0, and then we can determine lambda. So the exponent is known now. That's from the complementary function. Okay, so let's see how to determine the particular integration. So in order to get the PI, the Aileron deflection must be assigned. Now we assign it as delta A. And also, when t is larger than 0, so after the maneuver, after actuation of the deflection, we have delta A, that's the Aileron deflection angle, and the rolling rate is unchanged. So P dot is 0, no rolling acceleration. Okay, so then we can have just plug in those numbers. So P dot equals 0, and plug it into the governing equation. Then we have minus LP times P equals L delta A times delta A. And we know P is minus that part. Okay. And then we have the PI and the CF both, and we just add them together, so we get this solution. But you can notice the coefficient of the E is still unknown. We need to determine that through the boundary condition. What is a boundary condition? Which means when t is 0, the rolling rate is 0. The aircraft hasn't started to roll, so the p is 0. Okay, so we just plug in the time t is 0, and we know k is L delta A divided by LP times delta A. So that's the coefficient k. Okay, so just replace k with that equation, so we have the final solution. And so this is a standard method to solve this linear first order partial difference equation. And the procedure is we apply the CF+PI and the boundary condition. In the previous slide, we solved this differential equation through the standard method by looking at the CF and the PI. And the second method is called the Laplace transformation. And the idea of Laplace transformation is to convert or transform the differential equation into an algebraic equation. Okay, so just help you to remember what is Laplace transformation, and it's actually a integration of the original function f t. Okay, and there's a table used to do the Laplace transformation. And for example, we can see if the function is 1, it becomes 1 over s. Okay, so this table will be available, and you don't have to remember this table. But if you use it many times, you probably can already remember it. Okay, so now we can rewrite the governing equation into this form. And so the coefficient of P dot is 1. That helps us to do the Laplace transformation. And okay, so let's go to the table. And if it's P dot, the first derivative, it becomes S times L. So that's the Laplace transformation for P dot. And for the second component on the left-hand side is the function itself, so it becomes L. And on the right-hand side, and the function is actually 1, so the transformation is 1 over s. Okay, now we can do the Laplace transformation. It becomes this equation, and apparently it's the algebraic equation. And so the target is to solve LP, and we just combine the left-hand side, take out the common term LP, and then we just do some manipulation. We can have LP. So, and you can see LP equals L delta A divided by IX times delta A times 1 over S times 1 over a bracket S minus something. Okay, and so now we need to move to the table, and we don't see anything like 1 over s times 1 over s minus something, but instead we can say 1 over s is actually 1 if we do the inverse Laplace transformation, and 1 over s minus something is actually e to the power of at, and then we can separate the 1 over s times 1 over s minus something into a over s plus b divided by s minus lp divided by ix. So that's the idea. Now the target is to determine a and b. And how do we do that? We just expand the right-hand side and do the comparison with the left-hand side. And then we can find a equals minus b equals minus ix divided by lp. So that's the solution for A and B. And okay, so we can just simply plug in A and B into the LP. So we have the LP, and it's like this. And the next step is we need to do the inverse Laplace transformation to eliminate LP. Okay, and so if we do the inverse transformation, we can have P equals minus L delta A divided by LP times something. And you can see this solution of P is the same as from the method 1, the standard method. So till here, we should be familiar with the two methods used to solve the governing equation for the Aileron deflection. Okay, and as a summary, the way to solve the governing equations through Laplace transformation, there are a few steps. First, we do the transformation from which makes the differential equation into algebraic equation, and then we do some manipulation and find the Laplace transformed function, and eventually we do the reverse transformation. Then we will have the final answer. So that's the second method. From the previous two methods, we've determined how the aircraft's rolling rate p respond to the Aileron deflection. So it can be expressed through this formula. And now the question is, and we can see that's in the dimensional form. What is the dimensionless form of that solution? And it might be more interesting as a general solution for analysis. Okay, and in the earlier lectures, we know the characteristic time for an aircraft is named as tau, and it can be calculated 2m divided by rho vs. On the other hand, the dimensionless density, and especially in the lateral directional part, is expressed as mu2, and the expression is here. By combining these two, mu2 divided by tau becomes v divided by b, and we take this here, and we will use it later. And in the meantime, the dimensionless time can be written down as tau hat, and it is t divided by tau, the characteristic time. Okay, now let's see how can we make the solution p dimensionless. And so we take the coefficient separately. So first we look at LP times divided by IX, and LP can be written as CLP times half rho vs b square, and we can find the coefficients through the table we introduced earlier, and for Ix is small ix times mb square, and by doing some elimination we have CLP divided by Ix times tau. And the same for L delta A LP, and we will have this CL delta A divided by LP times mu2 divided by t. So we plug in these two parts, and we will find a dimensionless p. It becomes p hat equals p times t. Why p times tau is dimensionless? Because p has a unit of 1
or radian over second, and a tau characteristic time has a unit dimension of second. So p times tau becomes 1. So radian has a unit of 1. So that's why p hat is dimensionless. And then we can have the expression of p hat showing here. Everything is dimensionless. Okay. And so let's give an example. So the from dimensional to dimensionless is not so hard. Let's see example. So this graph shows Cessna and Cessna 172 aircrafts respond, how the rolling rate respond to the aileron deflection. And the horizontal axis is the dimensionless time, tau hat. So it's t divided by tau. And the vertical axis is p hat divided by delta A. Delta A is measured also in radian, and the p hat has a unit of radian or 1. So anyway, they are dimensionless. So we can see once the time, dimensionless time, approaches 0.5, the change in p hat or p hat divided by delta A converges to minus 4.2, about that value. So which means the response time is about half of the characteristic time of the aircraft. And for Cessna, the characteristic time is about 2.35 seconds. So which means the aircraft becomes stable after about 1.175 seconds. So that's how can we make use of the solution to analyze the aircraft response. In here is the rolling rate response to the aileron deflection. So you see it's a stable aircraft, the rolling rate will converge to a stable value in here. And the time is also quite short. It's very quick response. So that's for this lecture, and we introduce how to carry out the dynamic analysis, and we use an easier or simple example by deflecting the aileron and see how the rolling rate responds to the aileron deflection to a certain angle.